Good day everyone, and welcome to the Materials Technology series. I always say everyone optimistically as if there's more than one person attending the lecture. Anyway, you can see from the current, we're talking about stone and masonry today, and as you can see from the current slide, I'm sort of starting off with an anecdote, but although it's an anecdote, it's sort of important, certainly in the history of construction technology, in so much as what you're looking at is an obelisk, as you probably realize. This was mined from the ground roughly 4,000 plus years ago, and was probably one of the first truly prefabricated objects, construction objects if you like. It is a sculpture, admittedly. They were designed, obelisks were commissioned by the pharaohs, and their job at the time of construction was to mark the entrance to temples. So they were always commissioned in pairs, and they were sited on the east and west of the temple entrance to signify the sunrise and the sunset. They were mined in the hills at Aswan in the south of Egypt. That'd be about 400 miles south of Cairo, or Luxor, about half that distance, I think, where they would have ended up. And they were the hills outside Aswan were granite, obviously. And what the ancient Egyptians used to do was send out seers, S-E-E-R-S, to divine the right place to start digging. And once they had said where they thought there would be this perfect piece of granite below the ground, a lot of workers would go out and firstly burn off the topsoil and then start digging. And the way they would mine these obelisks was to dig two parallel-ish trenches and then work their way underneath between the two, propping with timber as they went, so that eventually they could excavate this continuous, pure, monolithic piece of granite. The way they dug the trenches is quite interesting too. They worked in pairs, holding a diorite ball, which is a very hard stone, on the end of a stick, and two men would work together, pounding the ground day in, day out for months, possibly even years, and they would do what you see in building sites across the world even to this day. You would see people chanting. They would chant to get a rhythm going, to get a kind of some consistency to their work and life. They would chant. This is known, and they were paid. They weren't slaves. They were paid in apparently beer and onions, among other things. And this was their day job. So day in, day out, they would arrive and they would dig, as I said, they would dig two trenches until the trenches were deep enough that they could start burrowing perpendicular to the trenches, propping with timber as they went, until eventually the granite was loose from the ground. The moment the granite was loose from the ground, they then had the problem of lifting it out of the ground, as it says there, and moving it up the Nile. The way they did this apparently was they of course the ancient Egyptians discovered leverage. They got very long tree trunks and logs to lever this huge monolithic piece of granite from the ground. They would then wait for the Nile to flood, which it did seasonally, as you probably know. They would place it in a raft of some kind, or on a raft of some kind, wait for the Nile to flood, and then move it upriver. And once it had got to the temple at Karnak or Luxor, they would then have to stand it up. And of course, this is still the subject of conjecture, how they actually managed to put these things vertically. Some say they built up hills of sand and kind of sort of gradually lifted them until they were in situ. Anyway, how do we know this? We know this mainly because of this. Some of you might be aware of it already, what's known as the unfinished obelisk, which is just on the outside of Aswan It would have been the largest obelisk by some considerable amount. I think twice as big as the largest one. But as you can see, here's the trenches on either side. What happened here was very tragic. Obviously, they'd worked on it for some months, probably years, had dug their trenches, and one day there was a chap working down here that just tapped his dolomite ball into the edge just once too often probably late on a Friday night, and this little fissure appeared, crack, and that was it. Good night. And they all went home. So there it is. That was Queen Hatshepsut. As I said, that was what? Now we're talking 3,500 years ago. Would have been a very large object, and it has, and there it resides. So we're looking at stone and masonry generally speaking. Stone, of course, it's the one of the oldest materials used for construction. It's also one of the few materials that tends to be processed on site. So what you're looking at here is an open cast quarry in the south of England, in Dorset. This is Portland stone. It's not granite. It's not what some people think it might be. It's Portland stone, but a very, very good building material for all sorts of different things. And what I was saying was that the thing about stone is that it's quarried, whether it's through a deep quarry or through an open cast quarry, and usually processed to the point where from the location where it's quarried it comes to your building site in whatever shape or form it has been commissioned to arrive at. Of course, as we know, it's a fantastically enduring material. It doesn't decay except over incredibly long periods, and for that reason it is highly sustainable, as I think I might have mentioned in previous lectures, not this one, that of course if you put a building together out of stone and it lasts 1,000 years, and you put a building together out of something else that lasts 100 years, you've already have 10 times the advantage in terms of the embodied energy of the material that you're using. So it is still a fantastically good construction material. Stone, though, strangely, this is what happens in open cast. Initially, you just claw. You can see here, you just claw away at the face of the quarry. You load up large, fairly random lumps, pile them up, and then you start to work on them. Strangely, stone, you might not think of it, but stone does have a grain. Almost all types of stone, not of course as linear as timber, but it is a grain nevertheless, and so you need to pay some attention to how you work it, how you cut it. Of course, sculptors know this extremely well. The first process for most quarries is to achieve something like this, which is just a rough stone, obviously, as you can see, which is guillotined. So this is a machine that effectively drops down under heavy load a blade here which just literally slices or guillotines the stone into rough pieces. That might be what you want. That might do. Particularly, sorry, I'm not working very well here with my PowerPoint. Especially if you just want a sort of dry stone wall kind of structure, that would do very well. But you can, of course, also cut stone, and this is effectively a saw. And this particular saw, which as you see is about 6 or 7 blades, I think, will slice a piece of stone into thin, shall we say, paving slabs. Here is a very large bandsaw, probably one of the largest in the world for cutting stone again. So you can saw it, as I said. That's the product of these kinds of machines, thin sliced pieces of stone. Another way of cutting them, again, one of the largest circular saws I've certainly ever seen. This is all local to this is all on site, if you like. This is where the stone is quarried, the stone is processed. You can be more accurate than all of that now, of course, because you can use lasers to very precisely cut the stone in the way that you might want it to be cut. Here we're still using a circular saw. This is not of course, this is not cutting stone with laser or water jet or anything else. It's still using, if you like, a primitive tool. It's more about the accuracy of the tool, and this is again very commonly used now in making stone components, and that's the kind of accuracy that you can now get with stone, with that simple, with that kind of process. Yes. So wherever you are in the world, this building material, which can go, as I say, from a very primitive, a very simple, rough sawn block that you haven't processed a great deal other than to split it in a fairly primitive way. And actually, I should go back just to remind you that one of the ways that they, although they were hammering away at that obelisk with diorite balls, they also did that process of splitting, where you make a small hole and you hammer a large timber dowel into it and wet it, and you might know what happens is that the timber dowel then expands and splits the rock. This was another process that was apparently used by the ancient Egyptians. This is the Portland stone that we were just the processing that we were just looking at. The Portland stone is, some people call it a marble. As I said earlier, it's not actually a marble. It consists of actually compressed, mainly seashells over many thousands of years, as you can imagine. So there's no, every single, if you like, piece of stone will have its own individual and different patination, which really can be quite stunning. Nay, abstract, should we say. Sorry, my computer seems to have gone to sleep. I really do apologise for this. Oops. It really has. Oh dear, what am I going to do? Oh, there you go. Yeah, same again. You can probably see here now. You can begin to see the detail that's going on here. These are, as I say, these are shells compressed over. It's a limestone. It's really a limestone. So yes, you can work it with your hands, of course. So beg your pardon, you can work it with primitive machines. You can carve stone as if a sculptor, and nowadays there are 7-axis robots. You've got 2 of them on your university campus at Marylebone that you can program to, with the right end effector, with the right tool at the end, you can program to work into stone, and in really fantastic detail, of course, according to the kind of stone that you need to use. I would, as generally speaking, since this is the first lecture in this series, we encourage in technical studies, we encourage you to use or to, if you like, experiment with machines to make things, not necessarily models, but to make one-to-one objects, because this is the real world. The machines that you have downstairs, the machines you have in this university, would be working in the real world, in industry. They'd be working flat out 24 hours a day in manufacturing something of use. And I think it's good to be able to make construction components, or see what you can do with the machine, experiment. We will always support you in this. Load test them, combine materials, if you like, load test them, and see what can be achieved. So, as I said, these lectures are going to be fairly short and to the point, just to introduce materials to you and to try and encourage you to work with them. If you can't literally work with stone, you can take a bit of breeze block or something similar, because you're going to have the same kind of, you're working with the same, you can do the same things geometrically with a softer material as you might be able to do with stone. This is the maybe again slightly anecdotal, but this is the Bell Rock lighthouse up on the east coast of Scotland. It's interesting because it's 200 years old now, and it's one of the earliest. It is one of the earliest stone lighthouses. This is one of a number of objects. I suppose we started with the obelisk that. Materials technology throughout history, the impact that it's had on design of the built environment cannot be underestimated. And very often the design of these objects, or the creation of them, is not the product of just maybe one person, but it's a product of a sort of cultural situation. Certainly the Egyptian one was of a belief that they could do things that somebody would have said, no, you can't possibly take a 50-ton piece of granite out the ground and stand it up. And here, this 200 years ago was at a time when a great deal of the shipping and trade around Europe and the world was floundering, and ships were being wrecked on rocks around the world, particularly, of course, around the UK. They were losing something like of all the shipping that came in a year, they were losing something really as much as 2/3 of it. And so lighthouses were desperately needed, and two things happened at the same time. One, the French developed the Fresnel lens, which enabled artificial sources of light to be projected huge distances. And two, this man Stevenson, his name was. There was a dynasty of Stevensons known as the Lighthouse Stevensons. There's a book of that name, written by Bella Bathurst, which I would really recommend using, was challenged to build this lighthouse on a piece of rock on the east coast of Scotland, just beyond Edinburgh, that was underwater for 6 months of the year. He was not a stonemason. Actually, he was an ironmonger, I believe, by trade. There was not so much a competition, but word went out that it would be great if somebody could do it, and he said, yes, I'll do it. And to cut a long story short, there it is. As I say, it was buried underwater for 6 months of the year. They had to build a temporary structure next to it, a timber structure. The workers that came out to work on it, it took them a few days to sail there. They used to get very sick. They spent months working. There was no energy other than the mules and the horses and manpower that managed to lift and put all these the stones into place. Excuse me again, beg your pardon. So here it is for most of the year, and here it is now, 200 years later. So here we are. There's the derrick, the timber structure that was made temporarily. Interestingly, they had to experiment, of course, to find the ideal geometrical shape. A circle on plan makes a lot of sense, as you would imagine. Again, looking at lateral loads from waves, to this day, it is an ideal way of deflecting wind and waves, of course, which is why the 30 St Mary Axe, the gherkin in London, is a very efficient structure in terms of the way it deflects lateral air. And it was built. This is a section through the foundation. So down at this level here, it was built on rock, so it didn't have to go down very far. They probably excavated a couple of meters below ground for the foundation. And then Stevenson decided that the most sensible thing to do, having decided on the circular cross-section, was to design interlinking stone sections so that there was no possibility of the movement. So this is the design at foundation level. What you're looking at here is a series of holes. These are actually dowels. So there are holes in the stone, and timber dowels were rammed through from one course to another just to stiffen the edge. This is for dowels for further up the building for carrying floor loads. So they carried timber floor loads across the building. There is the evidence of this is in the museum. I think it's the Edinburgh Museum. Will McLean will tell me whether I'm right or wrong when he listens to this lecture, but it's somewhere like that. Anyway, these are the original models that Stevenson created to explore this idea of the doweling of stone, which is unusual and radical at the time. The other thing just to note about this is that the profile is also critical. They found that I beg your pardon. Well, this shape here is actually a parabolic. And in physical structures that resist loads and resist gravity, it's often been found that pure geometric shapes, pure mathematical shapes, do work very well. Now that shouldn't be any coincidence, but it's true. So, and they discovered it in their case by constructing small scale models of the lighthouse and literally chucking buckets of water at them to see how different profiles and different cross sections would resist the load. So again, we encourage you to try out things, load tests, what if, and you can see here. So at ground level, at foundation level and ground level, it's just solid stone, and as you go up through the structure, the outer wall, the hollowing out of the center, if you see what I mean, gets greater and greater and greater until you get to the top. So it's an astonishing project. This is another astonishing project, which is much more up to date. This is the engineer Peter Rice. I'm sorry, it's not a very clear image. This is the engineer Peter Rice designing a pavilion for the Seville Expo, which I think was 1997. I could be right. I could be wrong about that. I'm not great on this, but anyway, he designed these. These are filigree, as you can see, arches, self-supporting arches that were designed for the expo, as I say, as a pavilion. They didn't have a great function, but they were just sort of proving a point, if you like. This is all stone, and these sections, all of these stone sections, these are, I believe, they're water jet. They're cut with water jets, so they're very accurate in the way they've been cut. Now, what you might be able to see, of course, we know that stone works very well in pure compression, so you can make an arch out of it. But to stabilize a structure as thin and delicate as this, what Peter Rice did was he made them bigger than you could possibly build with just normal stone. By the way, these are all dry joints. There's no mortar in between any of this. This is all dry jointing. But he's taken all the tensile loads out. Now, we know that all the tensile loads, we know that in bending that they are always in the lower part of the arch or beam, aren't they? So he's expressing that with these beautiful stainless steel delicate rods that are dealing with all the tensile loads on the structure. So it's a very elegant structure. Gonna have to keep doing this, aren't I? As you can see, a combination of pure water jet cut stone and stainless steel. So again, something we would encourage. It's structurally expressive. You can understand what you're looking at completely by looking at the structure. You can understand how and why it's working, why it's stable, why it's resisting load, although it's only its own dead load. There's no live load on this structure. It's all dead load, but nevertheless you can understand it. So again, the detail connection pieces will also be critical, will be very important, won't they? Oh, now what? Yeah, as I said earlier, I'm sure you know this already. All the compressive load is on the top surface of arches and beams, and the tensile loads are in the underside. So yeah, made the components, in some cases individual components, in some cases composite, such as this one, already put together with that. Now, isn't that beautiful? Again, this is so much what we would encourage, the way we would encourage you to think about construction technology. It's efficient. It's being built. This is being built off-site under factory conditions, so very effective. It's efficient because it's using a minimal amount of materials to achieve the maximum. It's taking all the loads into tension, so all the expressive loads are in tension. So you don't need great big. It's not the Parthenon. It's not classical use of stone. You're not using huge amounts of stone. So on a number of levels, it's a low embodied energy efficient way of putting buildings together, isn't it? Now I'm completely lost control of my slideshow. Yeah, there it is again. And also very elegant. I know, I do rather like that. So here, I suppose this is slightly the other end of the spectrum, but this is just to show that we're still building this way. This is a contemporary structure. This is I say contemporary. It's built about 10 years ago, I think, in Warwick. It's a new church, or so, yeah, built with load-bearing stone and brick. The columns are composite, as you can probably see here, so that there is actually a brick core here. Here's the stone that's been cut. These are this stone has been cut, as you can see again, water jet cut or extruded. They look as though they've been extruded. Of course, they haven't. They've been water jet cut. This is this is a low tensile building. There is no, we're not reinforcing this with steel. This is not concrete. This is definitely low tensile in construction. The columns are very close to each other. We there's nothing wrong. Again, we wouldn't dispute you wanting to put buildings together in this way. The reason for doing it would be, well, we've got a local source of stone, let's say, and a local source of clay. We have stone masons. We have people that can work with this. We will design this way. So it's classical, I guess, but again, I wouldn't have any objection if you can follow that through. The other thing that should be said about this particular project, and a lot of projects that are being built with masonry currently, is that, as you're probably aware, we'll talk in a little bit more detail when we talk about reinforced concrete, is that cement is something that's a very high energy, and it uses a lot of energy in its production, so that the industry is trying to minimize the amount of cement that's used generally in construction throughout the world. And there are a number of cement replacements, but one of which, certainly with not necessarily with concrete, but when you're working with masonry, clay bricks and so on and so forth, is to make mortar out of lime. There's absolutely nothing wrong with that. This building, this is completely uses lime in the mortar. Okay, so the lime hasn't been processed into cement. It's lime in its pure state. So I think the last project I want to draw attention to is this. Well, there's two interesting things going on here. One is, this is Foster, as you probably know. Again, this is Norman Foster's the forecourt of the British Museum in London. If it's open now, please do go along and have a look if you haven't already. There's some interesting things going on here. One is this lamella dome, not sort of lamella dome that they placed on the roof, which in itself is an interesting project, which I'll mention briefly. But this is a quadrangle, and there are 4 porticos, north, south, east, and west. This one I don't know whether it was demolished during the last war, or for some reason it wasn't there, and so Foster was part of his project. His commission was to replace it. So this is a new stone portico, built exactly as an exact replica as how it would have been built when it was originally built. What's interesting about it is that it is Portland. Well, it's not Portland stone. The quarry that I showed you earlier is where the original stone for this building actually did all come from. Came from Portland in Dorset in the south of England. But for some reason, either Norman fell out with the manufacturers, or he went across to France and he bought this stone. Now it's actually the same seam of stone. It goes under the channel, pops up again in France. It was probably just cheaper, so this stone came from France. I'm not complaining, it's beautiful. The other thing to note about it, though, is that now some of this was made by machine. Okay, was water jet, laser cut, what have you. This is not one continuous piece. Obviously, it's a series of sections. But up here, once you get to really get into quite detailed, these are actually hand cut. These sections along here, this fritting along the edge here, and some other fritting along that you can't quite see. I can't get enough detail here. Along these edges here. So there's a rough cut stone, and this is done on site. So this is put up in a kind of fairly approximate geometry, but rough cut, and then it was cut by stonemasons on site. And again, let's think about this. This is the beauty of that object that you're looking at now, is that it still requires both processes together. It requires the human hand, requires state-of-the-art CNC cutting digital technology, which is fantastic. Which brings me on to the roof, which is this is sort of not really about what we're talking about, but in a way it's just quite interesting. When they designed the roof, they looked at it on plan, and they thought, okay, we can make these fairly gentle. We can make a sort of a lamella dome, which, as you probably know, is it's almost like the double helix going in both directions, and we can make it span both ways. It's pushing against the reading room in the center here, and it's pushing against the existing quadrangle on the outside. So what they had to do to resist the pushing loads of the arches is to put a continuous steel ring beam around these edges. So there's a continuous steel beam around the whole extent of the and there's another one wrapping around the reading room. So actually it's pushing onto this continuous, it's taking the loads continuously, if you like, from around the building. So it's not actually taking any load onto the structure except purely vertically, which is all it wants to do. Now the problem was, interestingly about this, is that it's all very well. The lamella dome worked, and there was also kind of there was an additional reinforcing, which was, again, if you look at it on plan, was like bicycle spokes on a wheel going in both directions. So you end up with lots of triangles, which are all perfectly the same. But when they went to survey the site, they found, to their chagrin, that the reading room was not perfectly in the center of the quadrangle. It was slightly off by a few meters, or a meter, let's say. Now, of course, that throws all these calculations of the pure geometry into absolute chaos. What it meant in terms of the construction project was that almost every triangle was suddenly different, and this puts a huge change on that, on not just the cost, but the whole principle of the thing. Now, the reason it's interesting is that Arabs looked at this, who were the structural engineers, and they thought, well, we could calculate, we could optimize the problem and try and work out the minimum number of triangular sets for the whole roof, but it would take us we'd need 20 people that work on it for the next 100 years or whatever, something like that. And what they did was they went to University of Bath, who were beginning to work on parametric design. So this is one of the earliest examples of a parametric design, and I apologize profoundly. I'm not very good at this. The name of the gentleman at Warwick who actually came up with the solution, very clever engineer down there. I'll get back to you on it, I promise you. Anyway, I was privileged to be around when they demonstrated the software for this, and of course what they did was they took what you saw was the roof on plan. That you saw a circle, and you saw the quadrangle, and you saw the radiating bicycle spokes, and you saw the lamella dome structure. You saw in real time the computer software. So this is just a plan graphic. You saw them pull that circle slightly off center, and everything started to readjust itself around it. And what it was doing, as I said earlier, is it's optimizing the minimum number of sets of triangles for the sake of the production of the building. Anyway, that's a complete aside, and it's not to do with masonry, but it is it might help to illustrate the principle of parametric design, which is something I'm sure that you will be using in the future, but not just to make pretty pictures, but to really understand structural efficiency and optimization. Okay, thank you very much, and good night.